In section 7.5, you are going to encounter 4 different objectives. Those are the objectives here, 15, 16, 17, and 18. All of this is review from Algebra 2X. Objective 15, know how to write complex numbers. 16, you're going to add and subtract complex numbers. 17, multiply and divide complex numbers. And the last bit is 18, solve quadratic equations that have complex solutions. So let's just get started and look at the first objective of knowing how to write complex numbers. What you want to remember about complex numbers is actually made up of the number I. Complex numbers, though, typically are written as a plus bi. What it is, this is the real component, this is the imaginary component. So, for example, a complex number may look like something like this, 2 plus I, or again, 2 is the real number followed by 1 imaginary. Now, before we get into that, we want to talk about what the imaginary component is. And you want to also recall what that is. Imaginary is this. Whenever you take the square root of a -1 or a negative number, you create an imaginary number. So going forward, whenever we see the square root of a negative, we're going to rewrite that as an I. This first question here, they want us to verify that f of x has 2 zeros, I and negative I, by evaluating x squared plus 1 for x equals I and for x equals negative I. So they're saying this is that x squared plus 1 has 2 zeros. They're saying that the first 0 is an I. So if I put I in as a solution to see what I get, will it equal 0 on this side? I squared is what this becomes, plus 1. Now, what is I squared? Well, come on back up here and let's take the definition of I, and if we square both sides, we get I squared. That tells us I squared is equal to the square root of -1 squared is the number -1. So take away from this, and remember I squared is -1. So whenever we see an I squared down here, I'm going to replace it with -1. -1 plus 1 simplifies to 0. Thus, it is a solution. I would also check with negative I. So put negative I back into the equation. If I take negative I and square it and do plus 1, what do we get? Negative I squared is negative I times negative I, or I squared plus 1. By definition, we know I squared is the number -1. -1 plus 1 is 0. Thus, it is a 0 of this particular equation. Continuing on with the imaginaries, they want us to show that the square root of -5 is equal to I times the square root of 5. Fine, let's just take the square root of -5. So the square root of -5 looks like this. On this particular example, they want us to recall that I is equal to the square root of a -1. Any radical can be written as a composition of 2 numbers being multiplied. This is the same as -1 times a positive 5, which can be broken up into the square root of -1 times the square root of 5. Well, we know that the square root of -1 is actually the letter I, so you replace that with I, and you get this. This is proof that the square root of a -5 is equal to I times the square root of 5. Now this problem here actually jumps to the fourth objective of today, which is solve quadratic equations with complex solutions. You could solve this with a quadratic formula. You can also just use basic algebra. If you do basic algebra on this, first thing you would do is subtract 7 from both sides. You get x squared equals -7. Then you'd come in and take the square root of both sides. So x is going to be equal to, be careful, plus or minus the square root of -7. Now whenever you see a negative in the square root, all you need to do is you can take that out, replace it with an I on the outside, but you take it out and you're going to have, it's plus or minus I times the square root of 7. So there are 2 solutions to this. Again, I'm going to caution you, the most common mistake is people will forget the plus or minus right here. Now our first objective was know how to write complex numbers. I briefly touched on it already at the beginning of the lesson, that this right here, a plus bi is in the form of a complex number. A is the real component, b is the imaginary. So on this question here, they want to know, name the real and imaginary parts of this complex number here. The real part of this is the number -11, The imaginary part is the number 8i. On the second example, the real is the number 5. The imaginary is a 0i because it does not exist there. Now this example 2 again goes back to our fourth objective of solving quadratics that have complex solutions. Now be very careful. This one cannot be solved with basic algebra. There's no way I can ever isolate the x squared and the x into one term. They're not like terms, so that's not possible. Also, if you try to factor it, you would want to look at factors of 7 such that they add up to -2. And there is no such factors of 7. 7's prime, so that doesn't work. Therefore, what you'd have to do is the quadratic formula. So doing the quadratic formula, remember that A here is the 1, B is the -2, and C is 7. So go ahead and put that in the quadratic formula. If you don't remember a quadratic, it's x equals -b plus or minus the square root, b squared minus 4ac. The entire thing is over 2a. So when you plug that in, x is going to be the opposite of b, or -b, so a positive 2, plus or minus the square root of b squared, so -2 all squared, minus 4ac all over 2a. And as you simplify this, what you're going to get, x is going to be equal to 2 plus or minus, -2 squared is 4, minus a 28, and that's going to be all over 2, and that's going to give us this. It's going to be 2 plus or minus the square root of -24, the entire thing over 2. Now, you can actually simplify the negative here, by the way. So 2 plus or minus, pull out the negative. But then see if you can simplify that radical further. Is there a perfect square within the number 24? There is. A perfect square for that one is going to be 4 times 6 is what you can do for that. So you're going to have this is equal to 2 plus or minus 2i square root of 6 all over 2. Now this is a complex number with a real and imaginary component, and typically what they're going to do at this point is they're going to have you come in and actually break this up into 2 parts. It would be this and this. So when you break it up, what you're going to end up writing is going to be up here. It'd be 2 divided by 2 plus or minus 2i squared root of 6 over 2. And then do simplify this further, so that would give us 1 plus or minus I times the square root of 6 is going to be your final answer for that. So there are 2 complex answers, 2 complex roots, 2 complex solutions. All means the same thing for this problem. Now for some extra practice, if you would like to go ahead and try finding the solutions to this. Again, this is not factorable, and you can't solve it algebraically, but use this quadratic to find the complex conjugate solutions of here. One thing you want to remember is complex conjugates, so I'm going to have you pause the video, try to set this up, and I'll have the whole problem worked out. And then I want you to listen to the solution and why it's called a complex conjugate, because this is a review from Algebra 2X, but you may not remember it. So pause it and see if you got the right combination for this. If you did all the work, this is what you should get as a final complex number. It's 3 plus or minus I times the square root of 2 over 2. Now, folks, remember complex conjugate. What they mean by complex conjugate is this. If you take the number 3 plus I times the square root of 2 over 2, its complex conjugate is just change the imaginary component sign. So the complex conjugate of that is 3 minus I times the square root of 2 over 2. Again, that's just definition of complex conjugate. Okay, we're going to address the last 2 objectives of the 4. The second objective was add and subtract complex numbers, and the third was multiply and divide. This should be absolute review from Algebra 2X. Here are some rules just to remember. To add the complex numbers, just add the real components and the imaginaries. To multiply, it's going to be just doing the FOIL method or distribution. And when you do the division of it, you just want to break your final answer into a real answer and an imaginary answer. So let's go ahead and look at these 4 types of examples here. If we start with letter A, which says take z plus w, all you need to do is take the z, which is 4 plus 5i, and add to it the w, which is 2 minus 3i, and then just add your like terms together. So we have the real numbers, and then we have the imaginaries. This is just going to simplify to 6 plus 2i, and that's the answer. Now part B wants us to subtract, so let's take z, which is 4 plus the 5i, and subtract from it w, which is 2 minus the 3i. Be careful here, don't forget to distribute through. When you do that, we'll have the 5 plus 4i minus 2 plus 3i. And then you're just back to basic addition. So on here you're going to get 2 plus 8i. When you write the complex number, always put the real part first, followed by the imaginary component. Let's continue on and do part C, which is multiplication, z times w. This is probably the most lengthy process of them all. So let's take z, which is 4 plus 5i, times that by 2 minus 3i, and then do the distribution on that. We would distribute our FOIL. When you do that, we're going to get 8 minus 12i plus 10i. Careful, this is going to be a minus 15i squared. Just treat I like it was an x. It's just a variable right now. Okay, add your like terms here. What we have right here for like terms is there. So we're going to have 8 minus 2i. And then it's a minus 15i squared. What you need to recall is this. We know that I squared is actually equal to the number -1. Why? Because it came from this. It all starts with the fact that I is the square root of -1. Again, if we square both sides, we can now say I squared is -1. So you have to be very careful. Whenever you see an I squared that is not considered simplified, you must replace it with a -1. In doing so, we're going to get this. 15 times -1. This is really 8 minus 2i plus 15. 8 and 15 are real numbers that should be combined together. So the new complex number is 23 minus 2i, and that is what happens when you multiply these two together. Continuing on, part D is probably one of the quickest ones here. Take z and divide it by 2. So the z complex number is 4 plus 5i, and divide it by 2. The only thing they want you to do is to break out the real and imaginary components. So break that up and break that up would give you 4 over 2. Plus 5 halves I. Do one last simplification and write it as 2 plus 5 halves I. And that here is our final complex number. Now this next slide is actually a pretty cool trick, so I would pay attention to it. It is just multiplication of complex numbers, but there's a twist to it. If you notice this, they want us to multiply 6 plus 5i times 6 minus 5i. These two numbers are called complex conjugates of each other. And so if you are multiplying two complex numbers that are conjugates of each other, what you're going to find is this will hold every single time. What you can end up doing is just squaring the a value and just squaring the b value and adding them together, and it'll work. So if you want to listen up to how I walk through this, otherwise just fast forward and see what the right answer is. Based on this theorem, what the right answer should be is I should be able to take the 6 and square it and the 5 and square it and get the right answer, which would be 61. So if that makes sense to you, great, move on. If not, here's how it works. If I do the 61, I'm going to multiply all this through. So it's going to give me 36 minus 30i plus 30i minus 25i squared. These two i's here cancel out. The I squared is the number -1. So it's really 25 times negative 1, or 36 plus 25, which is the 61. So again, this will work every single time you multiply two numbers together that are conjugates of each other, which we're going to use in this next example. Now we are almost done with notes, but this next slide here focuses on the third objective of multiplying and dividing complex numbers. A complex number is not considered simplified if an I is on the bottom of it, just like a radical. You can't have, for example, in a radical 1 over the square root of 2. You have to simplify. Complex numbers have a similar property. So what we need to do here is come on in and get rid of the 5 plus I on the bottom. And the easiest way to do it is to multiply by its complex conjugate. So the I can't be down there, so what you do is you multiply by its complex conjugate. Because we know when you multiply by a number and its conjugate, the imaginaries drop out and you're left with a real, and we'll be fine. So it's 5 minus I. Now on a fraction, if you multiply the bottom of it by a number, you must keep it balanced and multiply the top. So unfortunately what we just did is we created for ourselves two sets of multiplication. Now, since we've been doing multiplication for a couple of slides here, what I would suggest you do is pause this and try doing the multiplication on your own to see if you get the right answer. And then I'll pop up all of my work. So go ahead and pause it and see if you can get the right answer here. Were you able to get this final number written in complex format? Again, just take a look at what I've done in this slide, the basic multiplication, and see if you made any errors on the own. And do break it into the real and imaginary components. Now this slide here just wants to highlight if there's three different polynomials you might get. And if it asked you to take a polynomial, which is all of these three here, and to factor them, theoretically they are all able to be written as factors, but they may not be factorable into integers. Now this first problem here, x squared minus 9, is clearly factorable. You can factor it into x minus 3x plus 3, and that would be the set of final complex numbers. The number 3 and number negative 3 are complex numbers. They just have no imaginary component. So they can be written as a set of integers. Integers are also considered real numbers, and integers are also complex numbers. Now this second one, x squared minus 5, it is not factorable, so it cannot be written as integers. But I can get the zeros of it and from there deduce the factors. The zeros of this, just set it equal to 0 and solve. The zeros are plus or minus the square root of 5. That's a real number. It's a decimal. So I can take those zeros and write them as real factors. Well, real numbers are also considered to be complex, so that's fine. Now this last one, x squared plus 36, it's not factorable into integers, nor is it factorable to get real numbers. But I can get the zeros of it and take those zeros and write them as factors. So x squared plus 36 equal to 0. You're going to solve. X is going to be equal to plus or minus I, square root of 36, which is the same as plus or minus 6I. So the two zeros of it are positive 6I and negative 6I. I can take those zeros and write them as factors. So these are the types of factoring you're going to encounter in all of Chapter 7. You know, in the last slide, just to make you aware of how the sequence of numbers works again is this. All numbers can be complex numbers, okay? A real and imaginary component. Most numbers have a real component in just that real component. Others have imaginaries. Again, imaginary is a square root of negative 1s. Real can't have negative square roots, so no negative square roots. That's the difference. Now, real numbers, remember from your previous math, can be broken into two different types of numbers, either irrational or rational. A rational number just means it can be written as a fraction, so something that could be like 3/4 or 7/10. Anything that can be written as a fraction. An irrational number is one that cannot be written as a fraction. They tend to be decimals that go on towards infinity. They have no repeating pattern. things of that nature. So like, for example, 1/3, that's a fraction, so that's a rational number. As a decimal, it looks like this, right? And it repeats. It has a repeating pattern, and it does go on to infinity, but it does have a repeating pattern, so it's not irrational. A number that maybe could not be written as a fraction but goes on forever, maybe you just have a decimal, and it goes on, and there's no distinct pattern, and it goes on forever. That would be irrational. The number pi is definitely irrational, okay? The letter E is also irrational. They go on towards infinity and have no pattern. Lastly, integers. We know that integers are positive and negative whole numbers. And then the natural numbers are just the positive numbers themselves, something that you would see in nature, more or less. The other thing I should highlight, though, be cautious. Integers also include the number 0. Natural numbers also include the number 0 along with them. Now let's just take a look at the homework assignment. There's a lot of good practice in this homework. Remember, you're covering 4 different objectives, but I will have you, I would say, you can skip 12 and just do 13 through 14 in that section here. And then I would ignore 27A because you're going to cover that later on in something else. And then you are going to want to add number 26 to the homework. This is a nice example of using the quadratic formula to solve something you're going to want to be able to do by hand. So good luck on the assignment.